All right, so this is Unit 8, Applications of Definite Integrals. I doubt you've been paying attention because you are a student and you don't think big picture. But we did derivatives, and then we did applications of derivatives. And now we've done integrals, we're going to do applications of integrals. So I thought I'd find a nice quote from Dante's Inferno. I believe this is the words above the entrance to hell, but we'll see how it goes. So what you should know at the end of this chapter, the definite integral is an accumulating function. We've talked about it accumulating area under a curve, but it can add up anything with a rate. And I'll give you some good examples on that. People getting in and out of line, all right? How do you calculate the area between two curves? We've actually kind of done this. You take one and subtract the other, so that's pretty easy. And by the way, I've rated all these on where I think they are: tricky, easy, goofy but doable, and then pure evil. That's my personal favorite category of math. So how do you integrate with respect to the y-axis? You got to turn things on its side. It takes a little getting used to, but it's not that hard. And then the pure evil one: how to calculate volumes using an integral. The washer effect and the circle problems are really not that hard. Some of the other ones they're just nasty. So that's okay, we'll get there. How do you calculate the length of curves? A piece of cake. Watch out for breaks and stuff like that. And then how do you apply it to science and statistics? Very easy, because I'm going to throw out statistics, which is not necessarily the hard one, the one that's just kind of a hassle. So no worries. So let's see what we got here. Suppose the initial, back up. All right, we're going back and doing stuff we've already done. Integral is net change, right? Remember the velocity thing where we take the derivative and we get acceleration, take the integral, we get position, right? Graph the velocity and describe the motion of the particle. All right, well, we've got, I'm gonna use some of the functions here. And get this out of the way. I've graphed y1, and I believe I've adjusted the window because I know what's coming. So I'm just gonna hit the graph and nothing's going to happen because I haven't turned on y1. All right, so we get this graph, does this, intersects at about 1.2, something like that. And we need to get up to 5. So it's 1, 2, 3, 4, 5. That works for me. 1, 2, I'm doing the sketch over on a separate sheet of paper. And the y-axis, of course, is all over the place, so we're not going to get into that. I have a feeling we're going to need the 0 where it intersects the x-axis. So we get this fun thing. Hey, what's the left bound? Bring our little crosshairs down, like a little spider crawling down a web. Now we're left, enter, and what's the right of that? You can see the little arrow at the top of the screen saying it's between these two arrows. And then they say, give me a guess, and it doesn't really matter, it'll take care of it. So that's at 1.255, and I'll write that down. And it's t 1.255 seconds. All right, let's see what we got here. So I wrote it down, 1.255 seconds. And yeah, 5 and the s seem to wash together. What are you gonna do? So this is your velocity. This is your time. We got 1, 2, 3, 4, 5. Notice it's really compressed, so you're gonna get some weird values later. Describe the motion of the particle. Okay, well, what the heck does that mean? Well, where does it go into the left? When is it going to the right? When is it standing still? So, straightforward enough. Left is from 0 to 1.255 seconds. Right is, and there should be no equal sign there, 1.255 less than t, and they only asked for the first 5 seconds, so up to 5. All right, again, there's no equal sign here. There's, do the horrible, yeah, anyway, standing still, 1.255 seconds. I'm leaving all my units off, just keeping it simple. All right, that's what we call displacement. All right, where has it gone? It went left, it went right, it went left, it came back to us. Its displacement is 0. What's total distance traveled? That's a totally different question. We'll get back to that. All right, so now we do this fun stuff. Suppose the initial position is 9. So we say, oh, well, to find position, given time 0, 0 to t, and I'm going to be lazy. I'm just going to write v of t dt plus 9. So to find this, we just plug in 0 to 1. And we plug in 0 to 5. So this will give me let's go back and use our calculator because I have it programmed in. So we get out of there, we go math, 9, 0 to 1, alpha trace, y1 is where it's programmed. It's all with respect to dx because that's our dummy variable, plus 9. So 5.3, what do we got? Centimeters. Now I'm actually going to put units in. All right, so let's think that one through for a second. It started at 9 times 0, it's at 9. All right, started at 9. And then we said it's going left. It's a losing area. It's getting more and more left. So for the first second, it drops all the way 5.33. At 5 seconds, I expect it's going to be way above because, again, this is a very dense y-axis. So it's going to stop getting negative here, and then it's going to get more and more positive to there. So I expect it to be a significant number. Let's be artful in how we do this. Enter, and let's just go fix it. Too far. 5. And we get 44 centimeters. 44 centimeters up here. All right. And I love it when I say things. I just tried to scroll down, by the way. I love when I say things like, we could use int. Yeah, we just did. All right, so without int, we would have had to say the integral of t squared minus 8 t plus 1 to the negative second dt equals t to the third over 3 minus 8 t plus 1 to the negative first over negative 1, positive, positive, and write that down here, t to the third over 3 plus 8 over t plus 1. That would be our antiderivative. And then we can plug that in and see what we get. Remember, we'd have a plus 9 out here, and then we'd have to put in 0, which would get us 0 here, but it would not get us 0 here, so it would get us 8. So you got a lot of things going on there if you were to do it by hand. So here's another example. Car moves at 5 miles per hour, accelerates at a rate of 2.4 t miles per hour per second. What? Yeah, okay. So let's slow down. Let's get this as our initial velocity. So how fast is the car going? What's the velocity? All right, let's go find a model. We know at 0, we got a plus 5 hanging out here. So we'll go 0 to t. Actually, call it x because we really should change the dummy variable. 2.4 t dt plus 5. So there's our model. All right. How fast is the car going after 8 seconds? 0 to 8. 2, that's a point. 0.4 t dt plus 5. We get 1.2 t squared plus 5. 0 to 8. Interesting. Yeah, okay. 0 is gonna cancel out. It's also gonna cancel out the 5, which is a big screw up. 5t, nice catch. Interesting, I believe I found a mistake on my, no, it's not plus t, it's just 5 because this is not inside the integral, we're not integrating it. Whew, having a rough day. All right, so the wall goes here, 0 to 8. 1.2 times 8 plus 5 squared gets us 276.8 miles per hour. Now we got a problem. This is miles per hour per second, and this was 0 to 8 seconds. Oh yeah, that works, no problem. All right, now the question is, how far did the car travel during those 8 seconds? Well, I'm not going to get into this because it's going to cause a problem, but we would do the integral, the absolute value of e of t dt, 0 to 8, but we'd have to do a lot of unit converting, and that's never going to happen on a real problem that we're going to be stuck with. So that would be our total distance traveled. Apologize for the mess. All right, let's try another one. So here we go. This is the point I made about, we've done velocity, we've done acceleration, we've done displacement, but we have not done other things. Well, of course, we're eating potatoes. And hey, we know that they're eating this many potatoes per year. Hey, it's a rate, we don't know how many potatoes. All right, so it's just straight up integral. So the integral, and we gotta be careful here. Since the start of 1970, so beginning of 1971 is 1, beginning of 1972 is 2, the end of 1973 is basically the beginning of 1974 is 4. Again, let's be lazy. There's no plus anything here. I'm just gonna put the plus 0 as a reminder because they're saying how much is going on over a span, not they'd already eaten 5 million of these things. How many more did they eat in addition? No, you don't have to do any of that, all right? So I'm going to nint this because I'm lazy and because integrating that would be quite a challenge. So let's go with math 9, 2 to 4. And alpha y2 is where I save this. Don't need anything at the end. We should get 7.066 million bushels. That's million, 2 M's. Love using words like bushels. All right, so the other way they can show it to you with a table. See this very commonly. Pump is connected, the rate at which pump operates, how many gallons are pumped. You would probably come to me and say, you don't tell me how to do this. Well, we don't have a function, so we can't nint it. We can't do an antiderivative. So the most accurate thing, if they don't tell you, is going to be trapezoid rule, right? Normally I would graph all this, 0, 5, 58, 60, so on and so on. But I'm actually getting pretty good at this now. So how many gallons? They didn't give me a function. If they did, I would say is the integral of that function, respect to time, from 0 to 60. So that just means go with trapezoid half. Is this a constant? 5. It is. 5. First one, 58, plus 2 times all of the other ones except for the last one. 60 plus 65 plus ... 60 plus 63 plus 63. And I have this handy. You should get 3,582.5 gallons. That's good stuff. Let's do a tiny bit of physics. And I do mean a tiny bit of physics. All right. Yes, that's an actual AP problem coming up, certainly. How do we calculate work? Well, first off, we say that force for like a spring or something is a constant, K times some X. So work is the integral, given the limits, of force with respect to x, as long as it's defined, right? So here we go. Here's the question you'll see, and I have actually seen this on an AP exam. F equals k times x. 10 equals some k times, if a force of 10 newtons, there it is, you stretch spring 2 meters, 2, divided by 2, divided by 2. My k value now is, careful, 10 newtons per meter, pardon me, over 2, 5 newtons per meter. Okay, so that means the force is 5 times x. The integral of 5x, stretching from 0 to 4, excuse me, dx, is 5 halves x squared, 0 to 4, which is 40 Newton meters. All right, notice the x squared. So we had a Newton per meter, meters squared, meters cancel off with a meter, work. You'll see this on your unit test, unit quiz, but you also may see something very similar on an AP test. So that's why I left it in there. And then one of my favorite AP problems. People enter line for an escalator. So now my brain went, oh, escalator, they're getting on the escalator, and all the people are coming up here and they're on the escalator and now they're gonna fall off. And my brain totally shut down. The funny part is, that's got nothing to do with the problem. People get online for the escalator. They're just getting online. Eventually they're getting off the line and on the escalator. Okay, it's a calculator problem. It's number 1 or number 2 on the free response. And looking at this, it's like, yeah, I hope it's a calculator problem. So they're getting in line at a rate. Right? What does that mean? I don't know what that looks like. I should graph it. Yeah, I'll get to that. All right. It's measured in people per second, times in seconds. And they get on the escalator. They also get off, and they're getting off at 0.7 persons per second. That's a little dangerous. Be careful with that. All right. At time 0, there's 20 people. Holy mackerel, they're doing all this nonsense. So we got to read the question carefully. How many people enter the line for the escalators during the time interval? So I don't care about them getting off. I don't care about how many people are on the line. All I care is how many people enter the line. So for A, that would be integral from 0 to 300. And this is where I get as lazy as possible. And I highly recommend this, by the way, R of t dt. Calculator time. Don't have this one programmed in. Planned ahead pretty well, but not completely. This one, of course, is a bear. 44 parentheses alpha y equals, enter. P over 100. We use x because it's a dummy variable. To the third. Watch carefully while you're putting this in so you don't make a mistake. 1 minus alpha y equals t over 300. To the 7th. Up out of there. Did I have to do that? Couldn't I have just put it in straight here? Yes, I could have, but it's not a bad idea. Math 9, 0, 2, 300. Alpha. I think we left that in Y1. Sure hope so. That seems a little on the high side. Matter of fact, I know that's on the high side. Question is, what did we do wrong? So it says, how many people enter the line, escalator? People enter line at a rate. No, that's right, 0 to 300. So the question is, did I put it in wrong? 44, t over 100, to the third, times 1 minus, times 7. Naughty, 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 naughty. Why did you people say something when I made this mistake? By the way, there's a trick here, second, right? Yeah, it takes me all the way there. Delete, and actually that's a good example. I should have taken a quick look before I ran off. Check my work. 7, enter. The good news is it is very quick fix. Enter, enter. 270, which is weird that that huge, nasty equation gives me that exact answer, but okay, whatever. So 270 people. Lovely. All right, let's keep going. During the time interval, there are always people in line for the escalator. How many people are in line at time t equals 300? So they're just testing your RTFQ ability. To save space, I'm going to throw it up here. How many people are in line at time 300? Well, there was, I suppose I should write it out. Integral from 0 to 300. R of t dt plus, there was 20 people in line started, minus the rate, 0.7 people per second times 300 seconds. Notice I put the rate, the units in because it is an AP problem. See what we get there. It's 270.7, need a calculator. 290 minus, I don't think I need a calculator. 330 times 7, 210, should get 80 people, which I would totally use a calculator for if I wasn't being lazy. All right, let's keep going. Let's see. For greater 300, what is the first time there are no people in line for the escalator? So calculus kind of just went right out the window. This is 0 up here. They're not getting in line anymore. The mall closed or something, I don't know. So minus 0.7 t equals 0. 80 over 0.7 equals t. That I'm going to use a calculator for, but I'm not going to show you. 80 divided by 0.7, I could actually do that somewhat in my head, but I'm sure I'd screw it up like I screwed up everything else. 114.286. Actually, I will share screen. There's no reason not to. So you might be tempted to write that down, but we got to slow our brains down. 114.286. All right, so t equals 114.286 seconds. Just wrote that down. Well, what does that mean? Well, let's read the question. What is first time t? There are no people in line for the escalator. So I'm going to go with t equals 414.286 seconds. I feel like I'm missing something here, but let's hope I got it right. And the last one, during 0 to 300, what's the time when the number of people in line is at a minimum? Minimum, maximum, I'm taking a derivative. Okay, what am I taking the derivative of though? They're asking me for not the rate, but the number of people in line at a minimum. All right, so the number of people in line is right here, I think. So we take the derivative with respect to t of 0 to t, because now we don't know, r of t dt plus 20, boxy thing here, minus 0.7 t. Derivatives cancel, and there's no chain rule, so I just get this cancels because it's a constant. This stays as minus 0.7. I get r of t minus 0.7. I have to set that equal to 0. So I'm actually going to go with r of t equals 0.7 and find that out and find out what that is. Now I actually have to go and check that that's a minimum by checking the derivative on both sides. I'm going to skip that just because it's going to take too long. Share screen. Y equals, let's go down one. 0.7, not 0.7 t, 0.7. Graph. Wait till it's done or else I'll crash my calculator. Good, that one's faster, thank goodness. Yellow thing finished. window. I actually don't want this. I want 300. And I guess I'll go to 10. I don't even need to go that high. I can go 1 and -1. Okay, so it's one of those two intersections. Which one? Well, here the number of people is going up. So I'm going to guess it's here. They're on their way down. Slope is, I'm just going to go with the second one. So second trace, intersect 5, enter, that's the curve, enter, that's the curve, and get a guess. First curve is off the charts, but that's okay. And we're going to go with 166.7547 seconds. 575 seconds. All right, now the fun part for me. And I tell people this all year long, and people do their best not to listen. That's great. It's what we do for a living. We don't listen to each other. We should be able to look this up. I honestly don't remember which year this is from, so let's go find it. Share screen, and let's go look. I think it's 2018. 2018 AP BC Calculus. You can see I've looked it up before. It takes me straight there, and let's see how I did. If it's not, oh, there it is. I got lucky. And I did get lucky. I really had no idea. All right, but what's at the end of it? Oh, they're going to make me do this nonsense. There we go. Now I know where to look. It's 2018. So let's double check. There it is. And let's go look at the scoring. See how we did. All right. So let's see. Number 1, 270. We don't have to write all this out. We put the integral and we put the answer, did we? Integral, answer. Yeah, we're gold. 2 points. Woohoo! Actually, let's do this backwards. So now for B, I got 80 people with the integral and the plus 20 and all that. So let's see if that is sufficient. 80, 20 plus minus, wow, I'm on a roll. They put the 0.7 inside. I do not have to. I would have gotten away with it outside. And it says, hey, considers rate out. So yeah, you're gold. All right. Part C, 414.285 seconds based on number of people. So now notice this based on part B. If you had a different number, you'd get a different one. So this one, they could care less what I did, as long as I got the right answer. 414.285 seconds. 414.286 seconds. Oh no, did I lose a point? Wow, 286, I was nervous. And then on the last one, total number of people in line, I did all this math, I got 158.07, and I should have used the first one, 33.03 seconds. 210, I have to go back and get it when there are 4 people in line. So yeah, I should have gone to the first one, I blew that, all right? But I considered that, so I got a point there. Yeah, no, I'd have to go and do the endpoints and all that, which I didn't do because I ran out of space. But let's see, what did I get? 1, 2, 3, 4, 5, probably has 6 points out of 9. I'll take that. It's not bad considering I was just fooling around. Oh, I'm not sharing right now. I just realized that. Apologies. So yeah, here it is. I went to T2 and yeah, that's a mistake. And also I didn't RTFQ. Says find the number of people in line at this time. So there's whole number of people. I just gave it time. So should have checked both of them. Should have checked at 0. Should have checked at 300. Again, I ran out of space, so I was kind of lazy there. Yeah, that's good. It's a good example of an AP question. That's it. Good luck.